Laurent gave you a little bit of an overview of structural modelling and a whole bunch of different things. I'm going to delve into a really specific part of it, and that's upscaling. And more particularly, I look at data density. And so as Laurent showed before and bastardised, I've got a nice little data set from Limousin area in France. And basically, it's really high data density. So there's a lot of data that's been taken. And my interest is whether we can take all this data, and if we can we create the same model using this? And so I've got Laurent Ayers as my supervisor and Mark Jessel as one of the people who's helped me a lot. And there's about 50 other people who could go on that list, so apologies for not being able to fit you on. This is just a bit of signposting about this presentation and what it's going to be. Uncertainties in geological modelling, which you've probably heard enough of by now, but I'll run you through quickly. Methods of upscaling. So I've done, as Laurent hinted at before, there's a whole bunch of spherical statistics we can do, which I'll run you through, which hopefully won't be too boring. Analysis of geological models, that's using geodiversity and a bit of 3D and 2D analysis. An application, which will be a look at the Limousin model and future work, so where the hell this is actually all headed. So the uncertainties in geological modelling are a heap. Some of them are related to software, and some of them are related to data. So we're never going to be able to take a data point every 2 centimetres and then create a model. What we do is we make the best with the data that we have. So we end up with a whole bunch of different uncertainties. We end up with uncertainties because we don't know where a data point is taken. We end up with uncertainties because we don't know how to go from point A to point B. And we end up with uncertainties because we don't actually know what's between point A and point B. And then we end up with a whole bunch of different uncertainties as well to do with topological relationships. As for methods of upscaling, there's basically a whole bunch of different ways to do it. So I approach it from the spherical statistics point of view and basically tried to apply a lot of techniques which have been used in other fields but not usually geology, and see whether they're able to take strike and dip measurements, orientation measurements, and then use them, maybe find out if the relationships that exist in spherical statistics can be applied to our raw data. Now I'll talk about analysis of 3D geological models. So Laurent before showed some cross-sections, and this is just, these are just 5 different models, and these are 5 different cross-sections. So as you can see, they're all very different. But the question of how different one is to the other, so there's obviously ones which is really different, but how do you tell how much different that model is to that one? Solid question. And then in application, these images have come out absolutely shocking, my apologies for that. But basically, we've got a whole bunch of data, we know what that model is. If we've only got a small amount of data, what does our model look like, and how different it is from our initial model? And then future work, and why I'm justifying spending my life doing a PhD. So uncertainties are introduced in the 3D modelling space pretty much at every stage. When you take a data point, you have no idea how representative that data point is of the local area. You have no idea how much data you should take, and you have no idea what's going on in a larger scale. It's only once you do modelling, or it's only once you put everything together that you can find this stuff out. So if you go out in the field and you find that you've got an outcrop, you are most likely going to take a heck of a lot of data points there because the outcrop is generally sparse. So is it worth taking all these data points? And if you put them into an implicit model, is it any more relevant than only taking one data point which is representative of that whole area? Which is, again, a really good question. There's limitations in data input. So the thing is, as Laurent showed before, I'm stealing a bit of Robin Arnott's work, and he's gone out and they've got all these beautiful maps with all these wonderful little symbols on them. But unfortunately, he's got all this data here, and that's reduced to this. Because that's currently what the current modelling packages that we use have the ability to take in. So we go from heaps of data to only a little bit of data. Is this enough data? It's a good question again. And then model topology. So we can play all these games for what faults terminate on what fault terminates, goes through which series, and this is particular for GeoModeler because that's where my project's based. But all these decisions have to be made regardless of the geological modelling tool that you're using. So upscaling can be done in a heck of a lot of different ways. I've focused on spherical statistics because it's basically a purely statistical method where you don't have to add any input. You can basically just set an algorithm and you can let it go. The research here focuses on orientation data, so strike and dip. So admittedly, there's millions of different types of upscaling you could do. So you can do upscaling of, in this model, we've got these measurements which are the orientation data, which are the strike and dip measurements. And the contact data, you could upscale your contact data as well. But in this case, all we've done is we've upscaled our orientation data. And some of them are statistically rigorous, so we can use quad tree methods, and then we can use spatially remove data, and we can say, after I've played all my games and tried to figure out whether these spherical statistics work, were they any better than just randomly taking away 10% of the data? So some of the methods of upscaling, which is just shown spectacularly there, is stochastic subsampling. So this is the most simple method of upscaling. So basically where you take an initial data set and you remove some of it. So this is apparently 5% of the initial data. So we had a really, really data-rich environment, and we took it down and we just randomly removed it until there was only 5% of it left. And here are 4 different models we get. So these are all just viewing in the exact same orientation, and these are 4 very, very different models. How do we tell how different each one is from the other? Is using geodiversity metrics. Then we can do some upscaling a little bit more intelligently, where we do grid cell averaging. So basically what we do is we take our initial data set, we put a grid over it, and then each cell of that grid we average the data. So just using spherical statistics, we can find the average of the orientation measurement as an average of the strike and dip measurement. So, and then we can go from where we've got really, really coarse scale. So this is a 5 by 5 grid. So we've got 1, 2, 3, 4, and 5. And then that's 10 by 10, that's 20 by 20. Again, apologies for the image. And then we get 3 different models again. Then we can start doing some really statistically rigorous analyses, which are a little bit boring, but actually give us a really good insight into our data points. So the thing we do is we do the Kent distribution, which is basically a Fisher-Bingham distribution for those of you who like your spherical statistics. And basically the most important thing that we can get out of this is what's called the kappa parameter. And the kappa parameter, like Laurent hinted at before, can be used as to identify the concentration of the data or to look at dispersion. So how far apart one data set is from the other in terms of its spherical statistics. So it doesn't take into account the spatial relationship of the data. So we just take all the data out of one of these small cells here. So we've got one data set, which if you look on your stereo net, plots all together. So they're all data points are all the same. Some which are slightly more dispersed, some which are further dispersed again, and then some which are even more dispersed. And we can see that this kappa value spits out something which we at least like tacitly. So we can see that for a start it seems to work. So here, where we've got all our data points at 1, we have a kappa value of 0. Here, we've got a kappa value of 0.78. So we've got and then we get the kappa value goes lower as our data gets more and more dispersed, and that's a little bit of exciting maths if you ever want to write something into MATLAB or Wolfram Mathematica. So there's other methods that we try to do. So when we hinted at grid cell averaging before, where we took a whole bunch of data and then put it into a single grid, a lot of the times when we take that average, we get issues because of outliers. So you'll have data that's being taken from different scales or data that is just an outlier because of the way it was taken. So what we use is we use the kappa parameter, which is the concentration measure, to identify and remove outliers from the data. So what we do is we take an initial data set, say this one, where basically we've got a whole bunch of different strike and dip measurements, and we figure out what happens to the kappa parameter as we take each of these individually away. So in the first experiment, we just take this single value away, and then we see what happens to the kappa parameter. Then we take this value away, see what happens to the kappa parameter. And whatever value changes the kappa parameter the most, so in this case, it's this one here, we consider that the furthest outlier, and we can remove that from our data point. So this is pretty brutal outlier removal, but for the sake of spherical statistics, it tends to be a pretty successful one as well. So what we do is we repeat that method that I just showed before, and then we find out what the increase in kappa is. And as that kappa keeps increasing, usually what we get is we get a break in the data set. And where we get that break in the data set, that's where we say there's in our case, moving from a data set like this, when we remove 3 data points, what happens is we get a large change in the kappa, and that's where we consider the largest outlier to have occurred, and therefore we're going to call everything that's this side, to the right of this data point, we're going to call in our inlier group. We can then do a whole bunch of other fun little things as well. So we're going to do quad tree logic, where basically Laurent showed before a whole bunch of coloured stuff based on the dispersion. And what we do is we say, if you've got a certain value of kappa, if you sit below that in your grid cell, you split it up further into different quad tree logic. So you can start with a rather coarse grid, And then if something's really close, so if your data's all really well concentrated, then you say we don't need to add more data, we don't need to split the bucket, as it's called in quad tree logic. But then you split it, and then you get this smaller and smaller you get your grid cells, the higher and higher this kappa value gets, the more representative we are of our data set. So what we can do is instead of just using the kappa value, we can also just use the number of points in the model, or we can weight the kappa value as well. So there's a whole bunch of different techniques we can use. Again, rubbish image, but the other option we do is vector similarity. So basically we do our grid cell averaging, we put a whole bunch of data points on our map, and then what we do is we say these data points are all really, really close together. So if you just take the average of them, there's only an average angle difference of 5.6 degrees. We say that only one data point needs to be in there. Rather than here, where we've got the average angle difference is 47 degrees, we say we need more data points here to represent it, because that's where we have less well-concentrated data. So this is another way to just identify outliers in the data set and identify perhaps more complex areas in our raw data rather than in our modeling scheme. We can then play with geodiversity, and these are some pictures I've blatantly stolen off Mark, which actually really exhibit what we try to get at when we say geodiversity. And geodiversity is basically a whole bunch of metrics in a model which can describe it quantitatively. So things like the volume of a lithology, or the depth to a certain lithology, or nearest neighborhood relationships. And there's basically any number of these that we can choose. And then we can compare different models and then show how different one is to another. And using a whole bunch of different statistical techniques, so principal component analysis or self-organizing maps, we can have a real quick look at what our most representative model is, or what our biggest outlier model is. So I'm going to really quickly touch on self-organizing maps, and this could actually be like 6 or 7 lectures in itself. And basically, a self-organizing map is an artificial neural network designed to produce lower dimensional data from higher dimensional data. So we start with a whole bunch of overlays. So in our case, we've got different volumes. So we've got the volume of lithology 1, volume of lithology 2, volume of lithology 3. And we can have a whole bunch of these different metrics. And we can use the self-organizing map, which is unsupervised, so we don't have to put any other input into it, to classify our data set. And so data that exhibit similar topological characteristics are grouped together, which is great. And we can use, there's a method to find outlier models as well, where we use this thing called the quantization error. So does this actually have an application after we've just spoken a hell of a lot about statistics? Well, hopefully. So we take this initial data set, which, as Laurent hinted at, I've actually got 1383, not 1389 measurements. But basically what we do is we take all this data and we say, we make no assumptions about the quality of our data, so we have no idea about whether this data has a confidence measurement attached to it. We just have every data point, and we say, can we upscale this in a way that will give us something similar to our original model? And these are just a little few of the geodiversity metrics that we used. And basically, so we've got, this is our initial model here. And so we've got a lithology 1, lithology 2, lithology 3. And you can see this is just the top-down view and plan. And so these are our 3 different volumes that we used. And then we use the surface area, or the contact between the lithologies as well. So we use a whole bunch of different metrics, and we put it into a self-organizing map. And we get some results which come out awfully, but basically we can show how closely related each metric is to each other. So we can see that the volume, this is just a PCA correlation between our different variables. And we can see, for example, that the volume 3 is really closely related to volume 2, but it's not related at all to volume 1. So there's basically a whole bunch of different stuff we can do here. But the most important thing, or arguably in our case, the most interesting thing you can do with a self-organizing map is you can cluster all your data together. So we use a Davies-Boulden index to try to identify how many clusters all of our data fits into. So it comes out with 6 different clusters of data. And so some of them, so cluster 2, these numbers, cluster 1, 2, 3, 4, 5, and 6, aren't any more closely related to each other. This is just how it's split up. So we see we've got cluster 1, which is our initial model, and then stochastic removal, which is just our random removal, at 50% of our initial data set and 75% of our initial data set. Cluster really well together, so that's a little bit worrying for us because it shows that if we were to do it randomly, it's better than if we tried to do it mathematically. And then cluster 2, which is our grid cell averaging, clusters quite well together. And then all the quad tree, regardless of the condition that we use to split our quads, all plot in the exact same cluster, which again is a little bit of an interesting observation for us. And then we get a whole bunch of weird outlier clusters, and these end up looking absolutely nothing like our initial model. So we take our initial model here. So if we were to visualize this, so if we just do our 5 by 5, so this is a really coarse grid, we see that we get something which has some similarities at depth to our initial model, but overall there's a lot of difference between it. Grid cell averaging, if we take that to a 10 by 10 grid cell, so we're making it slightly finer, we can see that we get a lot closer relationships, especially at depth. But we have this northern section here, which basically looks nothing like it. And then even if we do the grid cell averaging at a 20 by 20, so quite a fine mesh, we've still got big issues in the northern section of the model. But we seem to be getting stuff that's represented quite well. Probably the most interesting thing is that the two models which have really low quantization error, which we consider the most common models, or you can think of close to the Barry Center if you're using principal component analysis, are where we use the initial model, and where we use the quad tree, and we use the median value of kappa to whether we split our whether we split our little quad tree logic. So you can see these models are similar, but they're also different. So I think we've got these similar features, especially at depth, match up really well. But this northern section here, again, is very different. So in the name of trying to figure out why the hell that was, we saw that there's actually a really complex area up here on our kappa map. So what we did is we added a single data point there into our northern region, and we go back to having a model which nearly looks exactly the same. And so we've gone from 1383 measurements to 64 measurements. However, it also shows the importance of individual data points. So this is really interesting for us to show. We did our statistical method, and we were able to get a similar model, but adding one measurement brings our model nearly back to the exact same. So that shows there's a crap load of work to do there. And this is the future work of this. So we do 3D metrics, but it's also really important to look at 2D metrics. So basically, in our input data, we just put a whole bunch of really large-scale 3D things in. But you can put a whole heap of 2D things in. So you could take an infinite amount of 2D slices through this model and then measure how much of lithology 1, lithology 2, lithology 3 there were. Would that make a difference in when we put in a self-organizing map? It would, but the question is, how different would it be? Are there other statistical methods we can use for upscaling? So I used a really specific spherical statistic method, and that was just because it worked. But there's a whole bunch of other ones we can use. And the really important thing here is the importance of outlier data points on our final model. So when we do get a really a single data point that has a lot of influence in our model, how do we account for that? Is there a way to account for that? Hopefully we'll find out. Beautiful. So that's it. Yeah, thank you.